get started on part 2 of yesterday's puzzle, which was this guy, Jurassic Jigsaw, the big map puzzle pieces. Yesterday I left off rewriting part 1. Yeah, always forget to turn on Do Not Disturb. So yesterday I started rewriting part 1, and because I needed the entire map assembled. So yesterday my original solution to part 1 was just to find the corner pieces, which was considerably easier. I was able to just identify the pieces by the number of edges that they shared with all the other pieces. And it was a bad solution because it was like, it was not guaranteed to work, but it ended up working. And oftentimes that's good enough. But in this case, it wasn't. It ended up being a case where I ended up needing the steps that I skipped in the next half of the puzzle, which I kind of worried would be the case, and it ended up being the case. So went back and rewrote part 1. Took quite a while, actually. Ended up sort of poking away on it a little late last night, just completing where I left off yesterday in the stream, because I had to go walk the dog and eat dinner and things, as one does. So what I ended up with is I ended up in the spot where I have the full puzzle assembled, and funnily enough, it's fill map. I'll show you what the IDs look like, which is kind of interesting. So this is I guess what we can do is we can do fill map. So we can say map equals, and or I guess this would be, map equals. And then what we'll do is we will print the map. Is there a print map? Did I make a print map? I forget. Anyway, we can for y in map, and then for I guess for row in map, and for call in row, we can, I guess we can just log row join. Whoa, how about that? Will that work? Let's find out. Oh yeah, row map, we just want the ID. Oops. Map. Actually, here we're gonna need that, and we're gonna have I guess it's gonna be a tile, not a map. Okay, and then so let's see. Okay, so weirdly enough, my solution from yesterday spit out the correct answer, which is these corners. However, oddly enough, if you're paying attention, you may notice that it's actually kind of flipped and rotated, but it's still valid because the puzzles fit the same way. It's just sort of like you took a normal puzzle and then you just like flipped it over and then rotated it. But since that's a perfectly valid solution for this, it's fine. So you can see 1951 is the top corner. Then 2311, which in their solution was in the middle at the top, is in the middle of the side for us. And then 3079. It's the same tiles, it's just in a different configuration, so totally fine. And this is not going to affect, it doesn't affect the answer because we just want the sum of the, or the product of the corner piece IDs. And it's not going to affect part 2 because in part 2 they expect you to be able to flip the thing. Anyway, so just thought I'd show you that, and we get the same answer. One other thing I found is that I don't remember how fast yesterday's solution was, just finding the corner pieces. It was pretty fast. It was like not quite instant, but almost instant. In this case, it's considerably slower. I could probably find a way to speed it up. And that might be useful because it's friggin' slow, but it works and it produces the right answer. But 22 seconds, that's kind of abysmal. And it might make doing part 2 a little annoying. I mean, what I could do is I could cache the map by ID and rotation and flip value. Ideally, it would be nice if I could find the solution a lot faster. I'm not sure how I would do that though. So I'll give you a small overview of what I did in part 1, which was, right, so each tile can have up to 8 permutations, which is that, like, you've got the tile, you rotate it 4 times, and then you flip it and you do it the same. And so I've got this method here that just figures out the permutations of each tile. And then each tile also has a method to let you know if it fits with the tile above it and the tile to the left of it. I don't know which way left is on this video. And then what you can also do is you can also ask any tile which of its permutations fit. So it can test all its permutations and find the way that fits. The main thing here, I don't need these loops anymore, is this fill map, where you take in all the tiles. It's a recursive function, and you pass it the x and the y of the map that you're producing. So it defaults to 0 because there is no map. And it's a recursive function that basically will initialize a map if there isn't already one. And then it will figure out of the previous tile what the bottom and the right values are of the previous tiles in either direction. So if there's a tile to the left, so this is my left, so that's your left. If there's a tile to the left, it will figure out what the left value of this tile should be to match. And if there's a tile above, it'll figure out what the bottom value is of there. So it'll figure out what the top value has to be of that. And then basically what it does is it iterates through all the tiles, all the tiles in your collection that are still in your collection. It will create a new set of tiles without those tiles. This should be pretty fast, I don't know. It figures out what the new x and the new y are gonna be, so it'll increment x and mod it by the map length. Same thing with y, it will increment y if x is rolled over. There's probably a smarter way of doing that. I could maybe convert it to base whatever the map length is and add 1 and then read it out as a digit, and actually that's kind of a neat idea. Anyway, but it does that, and then it clones the map. This, maybe the recursive nature of this is where it's slow. It'll clone the map, and for every permutation that fits these new criteria, it will assign that permutation to the new map, and then call fill map again. So I wonder how many loops this is running. So maybe actually that's a thing I could do here, is I can check loops and then loops plus equals to 1, and then I can log loops if loops mod 1000 or unless. There you go. So maybe this will print out. Well, let's print out every 100 loops, and we'll run it on yesterday's puzzle. So it's less than that, but on the input or the test input, but on the real input, it'll probably log a lot. Yeah. Okay. So it's doing a lot of loops because there's 144 tiles. And that ends up being a lot of combinations. But this definitely does, I mean, there would be up to 144 factorial combinations. kind of wish it didn't have to look at so many, because we're already up in the 400,000 almost calls to that, which is why it takes 20 some odd seconds. It took less time, and I think maybe part of that would be, I think the same thing that is making my map result flipped is what's causing it to be slow, because it's probably designed. People are experiencing buffering. Well, I hope the stream is still going. Oof. Hopefully we're back now. Yeah, there we go. So hopefully the stream didn't drop. Okay. Hopefully the stream is still streaming. It's giving me warnings about the bit rate. Anyway, I'm just going to keep talking until the stream gets cut off, if it does. So one thing that I would like is, I would like to maybe solve why it is taking so many iterations. And one of my ideas for that would be to figure out why it's flipping. Sorry. Okay. Whoop. All right. Cool. So yeah, I guess why is that? So why is it doing this? Theoretically, the first permutation should be no rotation and no flipping. And I think, if I recall correctly, so it wants this. It wants to try this one first, and that one, whoops, that one is the end of tile 1951. So it actually wants to flip, I think, 1951 upside down. And maybe that's why it's having trouble, because it wants to flip 1951. And then this would be, this would be the top of 1951? It's the bottom of 2279, and it's the top of 1951. Yeah, so maybe that's why. Maybe if I try flipping it first, it'll go faster. So we could try that. And then I guess 2729, or I guess we should try maybe rotating it. Is that what the problem is? It's rotating first and then it's flipping. So one thing we can try is we can just try, in this permutation thing, what we do is we first rotate them and then we flip them. What if we try all the rotations and then we try the flips? So for rotation, and then for flip, we push the tile and then we flip the tile and then we rotate the tile. So what about that? Okay, so that takes a lot more iterations and then fails. That's interesting. Cannot read property 0 and define. So, however, let's see what it does for the second one. Let's see if it takes oh, we should turn off that logging every. Let's log every 1,000. We'll see if it. So okay, that's interesting. So it actually runs into an error on line 294, which is 294 corner tiles. corner tiles. Okay, so let's try just log fill map. Oops. Let's see what we get back. So false. So that's interesting that it gets a different result if we do these permutations in the other direction. So for rotate ID in 0 to 3, so we want to rotate 4 times, and then we want to flip twice. So for flip ID, so this would give us, we'd flip twice, then we'd rotate, then we'd flip twice. Oh yeah, that's, let's just write it out. Let's do, okay, so let's rotate 3 times. Let's just do it manually. So first we're going to push the tile as it is now. Then what we're going to do is we're going to push rotate. So that's going to rotate 90 degrees, 180, 270. So 90, 70. Then we're going to flip, and then we're going to rotate 4 more times. Does that make sense? And then we'll return push. No, it's tile, oh, flip V. Oops. So flip vertical. So let's give that a try. So that's also giving us the wrong thing. So this is when we were in, so let's leave notes. Whoops. Let's leave notes off to the side here about what state we're expecting to be in. So this is supposed to be rotation 0 and then flip 0, and then these are going to be flip 1. I see we already have too many flip 1s here. So this is going to be rotation 1, rotation 2, rotation 3, and then this will continue to be rotation 3, 3, 3, or 3, and then this would be 0, 1, 2. Interesting. So maybe, so it's, and we should always get 8 permutations. Oh, you know what we're not doing is we're getting the same thing. So we need to tile equals. R0 is not defined now. That should have been comment. Okay, so this is giving us a lot more iteration. Or no, this is okay. This is for part the bigger map. It's still a lot of iterations. I'm not sure that this is helping at all. I guess what we should do is we should run this assertion on the smaller map and see if it does anything. I'm just curious. I'm going to let it run and find out how many iterations it takes. The old one was almost 400,000. So if this is similar, then we've done absolutely nothing, which is honestly kind of what I'm expecting, because I think this is not remarkably different from the automated flipping and rotating code that we had earlier. Except I guess we were flipping first. So this is actually taking more iterations, which is interesting. And that may mean that we are just we're just taking more time. One of the things that could speed this up dramatically is if we sorted the tiles by their likelihood of being a corner piece. If we start with a corner piece, the rest should, that would eliminate a huge swath of tries. Okay, so I'm gonna back out of this and go back to the previous code, because at least that was running in like a semi-reasonable amount of time. And where were we? Yeah. flip those. Okay, so there we go. So let's go back. So we're gonna, every 10 loops. Okay, so I'm gonna stop this. We were over 1 million already. Okay, so, right. The old way, we had this idea of possible corner state. And what we wanted to do is we were essentially trying to find the maximum number of, we're trying to find tiles with the least overlap with the general set of sides. And those were our corner tiles. So one thing we could do to try and speed up the iterations is starting with a tile that we feel is reasonably likely to be a corner piece. Because if we start with one of the middles, we try a bunch of things and then we throw them away, and then we try a bunch more things and we throw them away, and then eventually we exhaust the problem space and we try a different tile in the first, because we do sort of depth first. And it was my hope that we would exhaust those quickly. But I think basically what's happening is like, we're kind of starting with like, maybe we'll start with one of these and then we'll build out these 2 rows, and then we'll get to the end and we'll be like, oh no, we can't actually do that. And so we'll start trying lots of different stuff, but that ends up being, you know, hundreds of thousands of permutations that we're trying. If we can start with one of the 4 corner pieces, at least we're guaranteed that we're not going to be backtracking all the way to the beginning, and we're very, very likely to go in the right direction. So that's what I'm going to try. I'm going to try and pull out this idea of a corner piece from the first time that I did this. So possible corner states. So what did we get? We got all side values. And that was basically like going through all the permutations, getting their top left, bottom right, and sort of like uniquing that entire set. And then for non-tiles, and we go through those, and then we look at the tile that we're examining, and we determine how many side values we don't have in common with that set. And the idea was that if we have 2 side values that aren't common, they must be a corner. And so that's what we're gonna do. We're gonna make a method here. And just call it unique, or let's call it common sides. And this can be the number of sides that it has in common with the entire set of tiles. So we're going to pass in common, where were you? There you go, common sides. We're going to pass in tiles, all tiles as an array. And we're going to do basically the same thing. So we get other tiles. And then what we're going to do is we're going to map. I guess what we can do is we can just collect sides. Oops. Other sides equals array. Let's just call this OS. Other sides. And then we can say 14 tiles when t isn't that. So we're going to skip this tile, and we're going to get all permutations. And then, so for p in t dot permutations, we're going to get top right, bottom left. And in fact, we can just do this. We can do sides, and we'll say top right, bottom. Oops, it's a function call. left. Cool. So we'll get all the sides and the permutations. It's going to have a lot of duplication, but that's okay. So OS, so this is other sides equals, and maybe we can just do destructuring to, so it's a p dot sides. That's going to make a new array every time. I wonder how long this is going to be. But then now what we want to do is, now that we have this big array of all the sides, what we want to do is we want to find out how many of this tile's sides. And I guess what we need to do is we need to sort of map on all the permutations, because the side values will change. So for p in permutations. Permutations is a method, so we'll need to call this. So for p in permutations, we're going to sides. I guess what we could do is we could make this just all sides. And before p in permutations, we could say ret equals ret. And what are we doing? Sides. And that way we can say t dot all sides. S. So it's going to be OS equals. We'll just steal this for up here as well. Cool. And we don't need this because we're already doing that here. And then this, right. So all sides. So now we need to basically figure out how many common sides there are. So count equals 0 and 4 side in all sides. We'll say count plus equals 1 4 side in all sides. So this is going to give us the common sides with the entire group. And what we want to do is we want to find where that's minimum. So let's see if this works. It may not, and then we'll have to debug it. Okay, so what do we got? Common sides, all sides. So let's just grab the first tile and see if, so it's gonna be tiles equals parse input, and then we can say tile 0, common sides tiles, and we can log that 8. And then what about 1, whoops, 8, 2, 8. I'm expecting some of these to have fewer than 8. 4, 8, 5, 8, 6. I'm running out of yeah, okay. I don't think we wrote this correctly. Okay, let's find out. Common. So where's common sides? Okay, so for T and tile, and T isn't this. Okay, so we want other sides. So we're going to destructure this and calling T dot all sides. So T for all sides. Oh, we're not whoops. We're not even filtering these. When S not in other sides. Or I guess when S in other sides. So let's try that. So we got 0. Oh, that's not good. Okay. 4T in tiles log. Okay, so that's not good either. So 4S in all sides. So this would give us all sides. Let's debug what all sides is. All sides equals all sides, and like log all sides Cool. So here, oh, maybe we need to flatten it. Log all sides. Whoops. Let's take a look. All sides. So all sides. Oh, I guess we should return the actual thing that we're making here. There we go. So all sides. It's still giving us an array of arrays. An array of arrays. An array of arrays. And why is that? Sides is an array. Oh, gotta spot that. There we go. There we go. Lots of repetition. So 16, 16, 0. That doesn't look right. 24, 16, 8, 16, 24. Maybe what we should do is we should unique them. So let's grab, I don't think I've pulled in any underscore stuff yet, but we should, let's do that. Let's grab unique. Let's grab flatten as well, because we'll likely use it. We can remove it later. Acquire underscore. So let's unique those. Coming back from here, unique array, and then what we can do is let's go as unique. Cool. There we go. So so this is common size, has 2 common sides, 0 common sides. That doesn't, yeah, this is definitely reading wrong to me. And all sides should have more values, and it is not. So let's see what we got here. Let's get rid of all sides. So wait, all sides. So what is all sides? All sides should give us oh yeah, we should be calling p dot sides. That's why. There we go. That looks more like it. So we've got 6 common sides, 4 common sides, 4 common sides, 8 common sides, 6, 6, 4. Okay, so let's log those, just those, instead of logging all sides. So 6, 4, 4, 8, 6, 6, 4, 4. So 4, 4, 4, 4. We've got those 4s are probably our corner pieces. The 6s would be the edge pieces, and then we've got 1, 8, which is our juicy middle. So what we want to do is we want to sort the array by common sides, basically. And then that will almost certainly start us with a corner. That's my thinking. Anyway, so let's do that. When we are doing this map, I mean, it'll still be trying to do corner, then corner, then corner, then corner, but those should be rejected pretty quickly. So let's sort these tiles. Let's make a thing to sort them. Sorted tile, sort equals takes in tiles. Maybe we'll come up with a better name for this. What are we gonna say? Sort by corner probability? I don't know. Yeah, all right. So we're just gonna sort them by common sides with tiles. Corner tile, where are we doing? Where's our sort? Okay, so tiles dot sort, is it sort by? Script sort function. Let me prototype. We can just pass a function to sort, right? Sorts the elements of an array in place and returns the sorted array. Okay, and default sort is ascending. Okay, where's us? Compare A, B. Okay. Cool. So we actually have to return, so we get A and B in, and we have to return A minus B. Okay, so sort, and then this is going to be A and B, and we can say A dot common sides minus B dot common sides. And then we're gonna, that will return, it will sort the array in place and also return it. But you know what, just in case it doesn't return it, I'm gonna put that in here. So, oh, and this should be tiles. Okay, so let's see. Let's say tiles equals, actually we can probably actually just pass this here, sort, and see if they come back in a different order here. And they do, 4, 4, 4, 6, 6, 6, 6, 8, 8. Okay, cool. So let's see how many loops we run now. So still 30-ish loops, and we're printing every 10. So let's print every 1,000 and run the, oh, we weren't sorting those. So sort parse input, that gives us our tiles back. Let's go back to sorting every 10. Oh, look at that, much better. Okay, so now if we parse input and we sort, I want to sort here. So I'm hoping that this will be considerably faster. So let's bump that up to 1,000. It can report every 1,000. And looks like the sort might take a second. Which makes sense because it's actually got to fill up all the permutations. So it's going to create 144 times 8 tiles. Okay, it still took 20 seconds. But it didn't do a lot of loops, which is weird. So let's say tiles equals sort parse input, and then it's going to be tiles, and let's log. Let's bring in time and time in because I'm curious. Time end equals console. I think it's console, isn't it? Yeah. So we're going to time sorting, and then we'll time end sorting, and then we'll time tiling. We'll time end tiling. Oops. So I was expecting this to be to be logging first, and I don't know why it's not. So sorting took 20 seconds, holy shit. And then tiling it took 165. So there's definitely a lot of work being done just in creating those permutations. And that's where the majority of the work seems to be happening. I wonder even without the sorting. Well, that's great news for us, which is that the sorting is taking a long time. So that means the tiling algorithm is reasonably fast. And if we can make the sorting happen a little bit faster. So one of the ways we can do that is we can memoize the common tiles, because it's actually just going to be doing that a lot. So where's common tiles or common sides? So at common sides or equals, we want a bunch of this stuff. So let's see if that is faster. So yeah, there we go. Now we're sorting in 2 seconds, much faster. Okay, so that's good. So that was slow. And then all sides we could do the same thing. We could say all sides or equals to, and then just do that and see if that's faster still. Probably, it's gonna save us a little bit. Okay, but you know what? We're in like the 1.5 second range or 1.9 seconds to do the whole thing. So I feel good about this. We could probably memoize some other stuff. Like I wonder how many times permutations is being called. So maybe permutations memo or equals. So this is going to give us this is going to trade memory for speed. So we're going to use a lot of memory, and honestly this one doesn't give us any real speed advantage because I don't think we call permutations that often, because we're also memoizing permutations that fit, which is, yeah, and we have to memoize this with an argument because of course each tile, actually I'm just going to put it back the way it was because each tile has to fit against these arguments. In most of these cases, like we don't actually care about the arguments. These are just initializers. Cool. Okay, so that's dramatically faster. So 1.5 seconds I can live with, and that's to solve the big case. I wonder how many iterations the tiling is doing for 144. It's doing 270 something. I'm all right with that. All right, cool. So let's put a pin in this because we can actually just do this all day, make it slightly faster. The sorting took longer that time. That's super weird. Why is that? I mean, not dramatically longer. I don't care. Okay, let's get rid of time and time end. So this is styles. Now we don't need that anymore. We can just sort. There we go. And we're gonna log that. The whole thing should run in a few seconds, including the assertion, and it does. So I'm good with this. So cool. Let's move on to finally. Let's move on to part 2. I don't even have a part 2. We can get rid of this old file at this point. This was sort of like my what if I want to look back at this kind of file, and we didn't care about that. So let's make 2.let copy. Whop. Bam. All right, and let's grab day 2 from over here. So day 2, I remember reading day 2 yesterday on the stream, and it was interesting. So it's basically like, okay, take what you did in day 1 and now add a bunch of extra steps to it, which is kind of funny. It's like, okay, remember yesterday? Well, today we want you to remove some gaps between the tiles, and then look for this, and then flip and rotate it, and then look for that again, and like there's rules about where they can be, and it's kind of cool. So and then you have to determine how rough the waters are in the sea monster's habitat by counting the number that are not part of a sea monster. In the example above, the habitat's roughness is 273. So that's interesting. Okay, anyway, so there's lots of good stuff to be had here. So that continues to be our input, and then we need to remove the gaps to form the actual image. So we're still gonna need this input. So I'm gonna be careful to cut around this input because we still want this. Here we go. So that's still our input. This is a plain block. All right. And this is also a plain block. There we go. That was a plain block. Plain. And then this is also a plain block. Actually, I think I have that. Nope. I thought I had it in my paste buffer. I did not. Cool. So we're removing the gaps from the actual image. Part 2. Okay. So now we've got, and then this is our input. And then after our input, we had all this crap that we don't care about anymore. Cool. And then, oh yeah, and our defs in part 1, we pulled this tile out so we could look at it while we wrote stuff, but we don't need that anymore, so we can remove it. Cool. And we'll do the same thing here. Okay, so we're still going to keep a bunch of this stuff because it's almost all useful. Oh, that was one thing I was curious about in part 1 before I move on, is we had this this fingerprint function that would turn each side into an integer, and it doesn't take much time, but I think it's pretty useless. So I'm kind of curious. So 2.6 seconds, if we just remove the fingerprint, A, does it still work? And B, how much time do we save? Any? So it's actually slower, which is interesting, because now we're doing string comparisons. So that's interesting. Okay, it looks like the fingerprint function actually does save us some time. I was not expecting that. I guess it's easier to compare numbers than it is to compare strings. So let's put that back. Let's cancel that. Let's try it again. We still, yeah, okay. Well, I guess we're keeping fingerprint then. I thought maybe we could remove it, but not so much. Okay, so back to here. Okay, so what are we doing? We're taking the map that we produce and then removing the gaps to form the actual image. So what does this mean, removing the gaps to form the actual image? Are we just joining the tiles together? So let's find out. 1, 2, well, let's take a look in here because we can count them easier. So 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 8. The borders of each tile are not part of the actual image, so start by removing them. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So they become 8 by 8. So we discard the sides and then we glue them together. Well, I mean, we got to start somewhere. We're going to start there. We want to shrink the tiles to the center by 1. So we want to discard the top, left, right, and bottom rows. Which means that when we're reading the tiles, so if we're reading them from our group of tiles to make a new map, a new mega map or whatever, we could just skip the last row and the last column as we're reading them out. And then we're gonna want to, so we're gonna make a new array. So it's like, that is the number of tiles times an individual tile length minus 2 wide. So, all right, let's make that function. So we'll remove all that. We can keep this, but we're going to create a new fill map. So map equals, and then we can log map. Am I in part 2? Yeah, okay, cool. So here's part 2. And what we're gonna do is we're going to need to make a new map, like a large map, like a chart. Let's call it a chart. Equals create chart map, Crete chart. It's a chart of Crete. Cart. Okay, create chart map. So we're going to create a chart from our map. And this is going to take our map in. And our map, of course, is an array. Just give us a little hint there. Okay, so we are going to make, this is going to be like similar to our blank map function. So let's take that and we'll just call it blank map, create chart. So this is going to give us, so we're taking in a width here. So let's make a blank chart, and we're going to take in a width because it's a square. So chart. Cool. So I guess we could just actually make blank. We could use blank map to do this. we don't have to create a new one with the right name. So because it's also a blank map that we're making. So we just want to make a new map. Chart equals blank map, and we'll call it map or length. So that times, so we want that to be individual tiles. So that times tiles length minus 2 times. So the map is going to give us like 3 by 3 in this case, and then we want to know 10 minus 2, so 8. So we want 3 times 8. Map, so we'll just find the first tile, dot or rows dot length. Is it dot rows dot length minus 2? Okay. So that's gonna give us an empty chart. So let's see what the empty chart looks like. Oh, it got angry. Cannot read property length of undefined on line 359, which is here. So map O. So this should be the tiles. Are we not passing in the map? We are passing in the map. Fill map. What does a map look like again? Fill map. Yeah, it's just a series of tiles. Blank map. Oh, you know what? It's not a series of tiles. It's a series of tiles. So we need 0, 0. Cool. There you go. So here we are. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 25, 28. 28? Is that right? No, that's not right. Times rows length minus 2. Okay. And then that should give us 24, I think, right? 1, 2, 3, 4, 8, 16, 24. Okay, perfect. So that's 1, 2, 3 rows of 8. So 24, and it should be 24 by 24. Okay, so that's going to give us a new chart, and now we have to fill the chart. So we can say for row in map, and then for, I guess we should say index, and for call, this could be row Y, and then for call X in row. What we want to do is we want to set the chart. I guess what we want to do is we want to say in, yeah, you know, we do want to do it this way. We want to do it tile by tile. We'll say chart. So Y. So chart YX. So this is going to give us, so we still want Y to be correct, and we still want X, but this is going to give us the base number. So let's think about what we're doing here. So we got so we're going to have 0, 0, and that's going to be our anchor point in the new chart. And then this is going to give us for tile, I guess, X. So this is gonna be chart X and chart Y and chart X. And then for tile Y in tile dot rows, so row Y, and then for cell X in row. Woo! So we're going to skip the first and the last of these. So continue if Y in either 0 or row length -1. So we don't want to we don't want the first or the last. We're going to do the same thing here. If X in cool. Otherwise, we're going to write this chart. So chart X, so Y times map length X times map length. Oh, this is going to be chart Y and chart X plus X minus 1 or Y minus 1 because we have the offset, and then that X minus 1, and then at the end of all of this we're gonna have chart. So that nuts? I don't know. Let's find out. Let's create chart. We're doing that. Log chart equals create chart map. Okay, so what do we got? It's breaking on line 364. 364 in tile dot rows. Do I have rows? I thought I had rows. Yeah, I totally have rows. Okay, and rows map row. Okay. For row in tile dot rows. So maybe I'm not. Oh, you know what? I'm overwriting row here. So this is going to be map row. All right. So we're still getting a lot of nulls. So this is not what we want. So continue if Y. Continue if X in row length -1. So that's, yeah, that's so in row for row in tile rows. So it's not CY, CX map length. Let's log some of these things. So let's log. Oops. Log that, and then we'll log that. So it's not logging these at all, which means that, oh, it is. There we go. 12, 10, 12, and we get up all the way up to 13, 13. Which would be, so 14, so that would be, that's not what we want. What we want is, for this example, we want to get up to yeah, we want 24, don't we? We want 888, 888. So why is it only going to 13? Let's find out. So Let's remove these and see if it throws an error. Should, yeah. But does it? -1. Oh, right. Let's hard code this value to 9. Oh, you know what? Row length -1. Yeah, so 9. Let's hard code this to 9 for now and see if it gives us a different thing. Let's also not log these things. Okay, so no, it's still giving us 13. So we've got our CY. So let's log. CY times map length. So let's do that. And then let's see what we get. So 6. So it should be 0, 3, 6. Yeah, okay, that makes sense. And then y is y. Oh, because we don't, we don't need to do the y -1, do we? Oh, geez, we're not assigning it anything. Okay, equals cell. So, I mean, that's part of the problem, but it's also clearly giving us the wrong number of things. So at least we got some stuff in here now, but we're still not. Okay, so let's let's go back to here. So we're still doing the wrong number of things. So for row in tile rows, so that should be 10. Let's log y here. And we should be 5, 7, 8, 9. Okay, yeah, so that's doing that. And let's try log x here. So we should have 8, 9. Yeah, we're getting 10 of those. So we should be continuing. Is it maybe what it is like it's break if. No. It just breaks out of the whole thing. Okay. So I guess why is it? So that, oh, it's times map length plus y -1. So, okay, we got, let's see, map length and then y -1. Let's try this. Okay, so we start with 0, 0, and that gives us 0. That's the row, and then we go row 1. Yeah, and we're going x up to 7. Good. 4, 5, 6, 7. So we're doing 0 through 7, row 0 through 7. And this is the first tile that we're in. And then this should be incrementing us to the next tile. So, oh, it's map length. That's not what we want. What we want is, we want, what was it? It's not map length, it's tile length, or rows, I guess row length. So this is going to give us the offset that we want to go in times map length. Wait a second, so that's going to be 3 plus 8. No, this is going to be tile length that we want, I think. So let's try that. Okay, so that broke, but it did get us to 24. Not rate property of undefined, but this is at least sort of getting us into the right ballpark. So 1, 2, 3, 7. Okay, but what's all this? Then we're jumping to 10. Maybe we want rows length -2. So this can be new width, and then times new width, and then this could be times the new width. Okay, this is what we want. So this gets us to an offset of 16 plus 7, which is 23, 23. Okay, cool. So that creates a chart, and now let's look at the chart and see what we got. This is not correct. We're still not setting it equal to self. There you go. Okay, cool. So now we got our new chart. So that creates the chart. And let's print the chart for cell in, or I guess for C in create chart. All right, we already have chart here. We shouldn't log it anymore though. I guess this is gonna be for row in chart. Log row join. How are they up there? They're just joined with nothing, I think. Okay. Cool. So this is our new C chart. Of course, our chart might be sideways. So let's take a look at the question 010, 1, 001, 01, 01, 001. Okay, so we've got that. And then 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1. Perfect. Okay, so it's our chart is sideways, but that's okay because we're going to be flipping. Cool. So I guess really what we want to do is we want to kind of want to have a tile for this that we can flip and rotate. So is there any reason why we shouldn't create a new tile, like tile dot was it tile parse? Yeah, because of the header. Okay. But all that does is it just makes this a new tile with ID and rows, so we can actually do that. Cool. So create chart. Let's do new tile. Come on. New tile. And it takes ID in rows. Yeah, okay. And this can be chart. Neat. So that's what that'll give us. And then what we'll do, rows, we'll need to do that. Cool. And then we've got our chart. Rad. Okay, so this is going to give us a tile. And now what we want to do is we want to make a method, I guess, on tile that looks for a subset of the tile. And so this is our sea monster pattern. So now you're ready to search for sea monsters, and this is what a sea monster looks like. When looking for this pattern in the image, the spaces can be anything. Only the used spaces need to exist. Also, you might need to rotate or flip the image before it's oriented correctly to find any sea monsters. Okay, in the above image, after flipping and rotating it to the appropriate orientation, there are 2 sea monsters marked with, oh, so we're gonna have to do all the permutations. And then what we're gonna wanna do is we're gonna have to search for sea monsters. So sea monsters are pretty wide. It looks like there's a limited number of places we're gonna have to find patterns. So a sea monster itself is like, let's see, 1, 2. So if this is 24, a sea monster is 20 wide. Not that that would be too computationally expensive, I don't think, but it certainly makes life easier because we can start with an offset of 0 and just move up to the offset of the entire thing minus the width of the sea monster. And so we can just check row by row. And same thing with the height. We can look from an offset of 0 to the offset of the height of a sea monster, which is only 3. So we'll only end up looking at 21 rows instead of 24. But the width, that'll actually save us a lot of loops. So now how do we check to see if the sea monster, to see if it exists? One thing we could do is we could just go over the squares in the sea monster, and anytime there is a thing on here, we can make sure that the corresponding offset that we're checking at plus the offset of the sea monster is also one of those symbols. And if it's true, then we found a sea monster. And if it's not true, then we haven't. So what happens if we find a sea monster? I think what we want to do is we want to mark the sea monster on the map. So if we find a whole sea monster, and it will have to be a whole sea monster, then we'll have to go through and we'll have to mark the sea monster on the map, which means physically removing these hashes, and we may as well replace them with O's. And then what we'll do is we'll count the hashes in the resulting map to see how turbulent the sea is, or the water roughness. Okay, how many blurs are not part of a sea monster? Cool, so there's our sea monster. Do we have, is he in here? Is he up here somewhere? Yeah, there we go. Sea monster equals. So here's our sea monster. And we don't have any dots, but we do have spaces. So this should be, I think this should be okay. So let's see what sea monster is down here. Let's for row in sea monster. Let's log row join. Boop. Oh yeah, sea monster dot. Yeah, we need to parse the sea monster. Okay, so let's do that. Parse monster equals, and then this is going to take text, and so for this is going to be text split on new line for row in. I guess we can just say that. Can we just map that? Yeah. Let's do text split map. And then this will be the row, and then the row split on nothing. So parse monster, sea monster. Let's look at parse monster, sea monster. Okay, so here's our sea monster. Cool. Isn't he nice? So, okay, let's log sea monster. Anyway, there you go. Okay. Whew. I'm cold. I'm gonna grab a sweater. I'll be right back. All right. And we're back. All right, so we got our sea monster, and okay, cool. So now, right, what are we gonna do? We're gonna go through here, and we're gonna have to. So we're gonna have to have a find sea monster. It's gonna take a map. I guess it's gonna take a chart and a sea monster. This is gonna be. I guess we're gonna call this Mark Sea Monsters. It's gonna take a chart and a sea monster. So this is going to. Okay, and that takes what is a chart and a sea monster. So mark sea monsters. So this is going to have to find a sea monster. So we're going to find a sea monster. Find sea monsters. Chart sea monster. And then so what are we going to return if we find a sea monster? We're going to return the X and Y of the sea monster. 4 coords in find sea monsters. I guess what we can do, so we're gonna have to be checking. We're gonna have to be flipping and rotating the chart. So we're gonna have to look in charts. So for chart, so for perm in chart permutations. And then if chords equals, so if we get back, anything from find sea monsters, what we want to do is we want to mark the monsters, return the map, return the chart, return the chart permutation. Okay. Cool. So find sea monsters. This is what we're gonna have to do now, which is find sea monsters equals chart sea monster. And what are we expecting? We're expecting back an array of coordinates. So like we're gonna be chords, which is an array. So we'll set it to an empty array right now. And this is what we're going to be returning. So if empty array, I think, is false. Yes, there's one way to test that. We can say log lol if empty array. If chords equals, and we'll like log lol. There we go, just to make the compiler happy. So now it's dot length. Whoops. Why are you like this? So yeah, an empty array dot length. So I'll say chords if chords length. Otherwise, I guess we can just say chords length and chords. And this can be and. There we go. So, right. So we're either going to return chords or nothing from here. So if undefined. So this should give us no lulls. Okay. No lulls for us. So sea monsters. So I guess, you know, we don't really need to parse the sea monster. We can parse the sea monster. So let's just do that. Let's just make the sea monster here. in fact, we can just, we don't need to pass it in. The sea monster is static, right? And we don't need it there. We only need it here. I guess we will need mark sea monster here. Here, sea monster equals that. And we'll do the same thing here. We don't need to pass sea monster in. Sea monster is a known quantity. It's a constant. Loch Ness Nessie is a monster, is a constant monster. Okay, so we've got chords. I guess we can just throw this in an initializer. Why not? And what are we doing now? So we're going to say for row in chart dot rows. And we're going to continue if index, so if sea monster, so the longest row in sea monster, which is, yeah, sea monster, I guess since sea monster is a known quantity, I don't feel terrible about this. So if index plus sea monster, the second row's length is greater than, was it chart row or row length? So row length is greater than that. Okay. Okay, and then for cell in row, cell and index in row. Oh, this is row index, or you know what? Let's call this y. Row is y, and then x. Cool. For cell x in row. What we want to do is we want to see if sea monster xy is, hey, does parse sea monster, does that, yeah, that splits it up on nothing. So we want to see if sea monster when, I guess what we can just say is cell is sea monster yx is x. We want to see if they're all, oh, it's not an x, it's a hash. So we're gonna want to, if these are all a thing, then it's true. So what's the break condition? We want to, I guess what we really want to do is we don't want to go through the, I guess we do want to go through the chart. So for every chart, we need to make sure that all the sea monster X's are there, or hits are there. And what does it look like if we have a false? So if there is, so for, okay. So if sea monster xy is that, then we want to return false if unless was it cell is. So now what we're doing, so we're going through every cell in the chart, and if the sea monster has a hash there, then we want to ensure that the chart has a hash there, and we return false unless the chart has a hash. Okay, and so that's our only failure condition. Is we're looking for CMonster, and we come across a thing where CMonster should have a thing, and if the chart is empty, that means it's not a CMonster. Okay, and cool. If we get to here for cell X in row, so for row, so continue. So this, oh, this is going to return false. What we actually want to do is we want to, I guess what we need is we need an is CMonster. Is CMonster. And that's going to take chart and a Y and an X. And whoops. So is CMonster. It's going to take chart X and Y. And that's, we're going to take all this stuff and we're going to put it in here. Is CMonster. So for row in chart rows, we don't care about this chart rows. What we care about, so that goes up, back up here. And we actually want to continue to do this. So we can return, we can do this in is CMonster. Let's continue if row, whatever. So cell is going to be chart rows, and we're going to start in the chart at this point. Yeah, okay. So is CMonster. So at Y and X. So chart rows Y and X. So for Y row Y so this is going to be Y offset. So really what we want to do is we want to do for the length of the CMonster, for the height of the CMonster, the length of the CMonster. So for CMonster row in CMonster, and for CMonster cell in CMonster row, and then this can be CMonster X, and this can be CMonster Y. Okay. All right, get out of there. And just off. Okay. Off. It's like I'm telling my dog to stop eating a porcupine. It's like off. Okay, so this is, we want to return a false. Okay, when some cell is, so we only want to check the CMonster. We only want to check the CMonster hashes, and we want to return false unless okay, unless chart Y plus CMonster Y, and then X plus CMonster X. Okay, otherwise true. That was a CMonster. So okay, for Y in chart rows. Okay, and in this case, what we're doing is we're saying, oh, continue if, we can do that in is CMonster. We can say continue if CMonster Y
or what do we want? We want to continue if y plus cmonster y plus cmonster y is greater than chart length. Oh, wait, y plus cmonster y plus cmonster length. So we want to say, okay, if our offset so this is how tall it is. Okay. If chart length, so chart length, that's how tall the chart is greater than the offset that we're checking plus the cmonster offset. Oh, we don't care about that. We care about the cmonster length. So we can just return false. Return false. Yeah, and we can return false if, I mean, chart length is the same because it's a square. A is greater than x plus cmonster 1 length. Okay. Otherwise, we'll check all the things, and then we'll return true eventually if none of these things are false. Okay, so is cmonster. So now we're going, okay, for row and chart rows, for cell, if is cmonster yx, and then was it chart yx. What we want is we want to chords dot push yx. Okay. Then we'll return chords. So let's find cmonsters. Now mark cmonsters. So let's log chords just for now. So this is mark cmonsters, and we take in a chart. Okay. So what is it again? Mark cmonsters. Mark cmonsters. No, it's find cmonsters. But for right now, mark, we're just gonna write down the coordinates. I guess we can just yeah, because that does for perm and chart permutations. So yeah, mark cmonsters. Let's get rid of all this crap. Chart and then cmonster. We don't care about cmonster anymore. Let's just run it, I guess. Cmonster is not defined. On line 384. Cmonster. And we don't care about cmonster anymore, do we? Find cmonsters. Is cmonster knows how to find a cmonster. Okay. What are we gonna, property 18 of undefined on line 399. So 399, unless, so it didn't like something about 18. So I mean, there we go. So it's not finding any cmonsters. So let's put some log is cmonster, and then x plus x. Whoop. So 2341. So it shouldn't be finding any c. Oh, this is looking in the actual input, not in the. It's looking in the test input, which. Does it have a cmonster in the test input? Chart, create chart map. Is cmonster. Oops. So, I mean, these should have defaults, but I mean, they'll have those anyway. So it's weird that, okay, so we're looking at, here, let's just go right back up to the beginning, 0, 18. So 18, that's weird. Why are we starting there? 18, 19, 41. So this is, I mean, this is wrong, what we're doing. So CMonster X. So somewhere in here we are, so Y and X are 0. Return false if chart length, okay. Oh, I see. So SM cell. I guess we're doing when SM cell is. So 18, 19, 20, 21, 22, 23. So that's weird though, that this is in the row. So that's giving us 18, but then Y is CMonster cell is whatever. So this is giving us some weird values for what a CMonster cell is. So this is saying that, you know, rows 18 through 41, or columns 18 through 41 are active. So we got for CMonster row, CMonster Y in CMonster. And then for CMonster cell in CMonster row. Oh, you know what? This is reducing the size of it, which we don't want to do because that'll throw off our index. What we want to do is we want to continue unless, okay. So now it's still doing the same stupid thing. So it's still starting at 18. Log. Okay, so we got CMonster X is always starting at 18, which is super weird. So 18 and then X. That's checking a lot of things. And I guess what we want to do is we want to continue if chart length is greater than X plus CMonster 1 length. So this clearly isn't working because CMonster 1 length. What is CMonster 1 length? Log. So let's find out. So 20. So this should be shortcutting for values of X that are above 4, and it's not doing that. It's still calculating 5, 6, 7, 8, 9, 10, whatever. Super weird. So it should be returning false if chart length is less than. So that, let's see if that gives us a better thing. So 0, no, it's still giving us big values of X. So let's rephrase this. If X is greater than chart length minus CMonster length, and then that should be the same as Y is greater than chart length monster length. Y is not defined, so capital Y. How about lowercase y? So it's still giving us the same bullshit. which is that it's like checking all the.
So this is checking all the values of x and probably all the values of y as well.
And it should be. Okay, so for CMonster X, so in CMonster row, so this should have prevented us. So chart length. Oh, these should be pluses maybe. No, chart length minus CMonster length. So this should be, yeah, let's log this. Log chart length minus that length. Not a number. Well, okay. What's chart length? Undefined. What? Oh, rows dot. Okay. Chart rows. Lol. Okay. Not working. Okay, no, it is. Okay, look at that. Okay, so it's doing far less work now. Any CMonsters. Okay, so that's for perm. It should be, oh, maybe it is, and it's just we're just logging so much shit that we can't see it. Nope, it's not. Okay, so for perm, let's log perm perm.id and then perm.r and then perm.f. So let's see if it's actually checking them all. Yep, perm chart. Good. And if coordinates equals find CMonsters, so find CMonsters. Oh, chart perm. God damn it. Every fucking time. All right. Okay, chords. Let's find CMonsters perm. So this should be getting sending in the permutation of the chart. And then for row in chart rows, for cell if CMonsters chart. So let's checking log xy. So this is checking xy. Okay, cool. So this is perm chart 0, checking 0, 0, 23, 23, 23. Okay. So 23, 23, and then it moves on to perm chart 1. Okay, and it didn't find any. So continue, return false. So let's make sure that these are right. Let's log and log. Oops. Come on. X. There you go. And make sure that these aren't going out of bounds. In fact, yeah. Okay. And I'm gonna remove that checking. Okay, so these should all be within the bounds. So within 2022, 22's not quite in the bounds. So 18, 19, 20, 21, 22. So I'm expecting it to be checking 4, and it's not checking 4, it's checking 5. Why is that? 1, 2. So let's take a look at our CMonster chart up here. Or actually, you know what? It's over here. So 1, 2, 3. I guess there are two more. So yeah, 1, 2, 3, 4, 5. It should check 5. And then it moves on to the next. And then how many rows does it check? It should check about 21 rows. That makes, or 22 rows, because it's 3 high. So it would start here. Yeah. Okay, so that makes a bit of sense. That makes sense. But it's not finding a sea monster. And it is checking all the permutations. So let's, where we're returning true, if, let's log, oh my god, or let's just oh my god it, and it'll blow up. Okay, so it's never finding it. So that's not good. Why is that not good? So return, it's always returning false. Is it blowing up here? Yeah, it is. It's saying cannot read property 18 of undefined. So 18 of undefined. 018. So it's saying the chart rows. Lol. Okay, reference error. Chart is not defined. How about chart? Okay, so now it's saying, oh my god, it's not defined. Okay, cool. So it's found a sea monster. Beautiful. Okay, and let's get rid of these logs. Okay, so it found, hey, chart 00, it found 2 and 2, 2, 2, and 16, 1. And that is correct. Okay, cool. So it's finding sea monsters. And so find sea monsters. Okay. So if it finds any sea monsters, right now we're just logging them, but we want to return coordinates. And here at the end of find sea monsters, we're going to be returning coordinates. And where's, oh, that's mark sea monsters. Find sea monsters. And that's what we're calling mark sea monsters. Okay, so we should log that. Somewhere in here we're logging this guy. Yeah, all right. So these are our sea monsters. So that's gonna find the sea monsters. So mark sea monsters. If coordinates, okay, then rather than returning the coordinates here, now what we have is we have a perm and a sea monster. Cool. So actually we could put this into find sea monsters and return. Nah, this is fine. Okay. So if coords equals find sea monsters. So we've got a list of coordinates for chord in chords. What we want to do is we want to mark sea monster. Okay, so this is what we're gonna do is, okay, for each chord in chords, so we're gonna add an offset. So this is okay, so what are we doing? We're gonna get the permutation, and we're going to get this is gonna be like yx equals chord. I guess we can just do for yx in like that. Okay, so this is going to be our general offset yx. So we're going to have perm x. So that's a sea monster. So now what we have to do is we have to grab a sea monster. And we're going to say for sea monster row in parse sea monster, and for cmonster cell in cmonster row. Okay, so and this is going to be cmonster y, and then this is going to be cmonster x. This is very similar to what we're doing any other place in cmonster row. And we'll continue if unless cmonster cell is that guy. So what we're going to do is continue unless cmonster cell is that. Okay. What we're going to do is we're going to grab perm xy, and we're going to, so it'd be y plus cmonster y, x plus cmonster x, and we're going to set that equal to, and at the end of this, we're going to return perm. Cool. So mark cmonsters. So this is going to give us a chart back. So let's see what this gives us. It blows up. Cannot read property. Cannot set property 20 of undefined. Is this chart rows? It's the same fucking thing. Perm rows. Perm rows. Okay, there we go. So do we have any, oh, oops, gotta run it. There's gonna be so many, oh yeah, there's some cmonster, beautiful. Okay, cool. And we should have some up near the top as well, and we do. Beautiful, so we got this chart. And now we get our turbulence coefficient. I'm just giving it a fun name at this point. And that will be chart. Cool. I don't know why that's there. Okay. And our turbulence coefficient of the chart will be like for row in chart dot rows. So we'll say turb equals 0. So here we can just put that in here. Chart turb equals 0. And then for cell in row, turb plus equals 1 if cell is choppy. Cool. And then at the end, turb. So turbulence coefficient, and what are they saying? We're saying 273. So we want to know the turbulence coefficient of Mark cmonster's chart. 273. Beautiful. So assert 273 is that. And a chart is just that. Create chart map. And a map is just that. So here we go. And so log parse input, and instead of input, it's require input. All right, it is 3:30. I hope this works because I actually need to take the dog out. It's funny how that happens every single day. There we go. 1909 is our turbulence coefficient. That's the right answer. 1 gold star closer to saving our vacation. Cool. We can return to the advent calendar. Cool. So that was day, was that 20? Day 20? Yeah. And day 21, I'm going to maybe do later. I'm going to either do it later or I'll do it tomorrow. I don't know. There's a lot of days left in December. Certainly not going to be doing this on Christmas Day. But I do intend to do them all. So, okay, cool. That was day 2. We can return, we can kill that. So let's what we usually do now is we go through and like clean up our code and talk about it a bit and refactor it a bit. And I might do a refactoring step at some point. Just, you know, things like this. We don't need to condense this quite so bad as we did. Rotate fingerprint. We ended up using fingerprint. We ended up using unique, yeah, but we didn't ever use flatten, so we can get rid of flatten. Pretty sure. Yeah, so unique flatten. Okay, same thing here. We can say flippy print. We're not really printing these anymore. Unique flatten. This all tiles cache map. We reset every run. Not a big fan of that, how that works. We could probably change that. Still runs. Yep, in 2.5 seconds. And then how long does this take? 2.5 seconds as well. It's mostly parsing that giant map. Cool. Okay, so yeah, we can get rid of some of these log statements. Yeah, log. Cool. Log. Oh, I got some logs here. Log. Yeah, we're not calling print anywhere, are we? Fingerprint. Print. Fingerprint. Yeah. We can get rid of these prints as well. This is just printing the tile. Oops. Find print. How about that? Keep going. There you go. Everything else we're using still. So common sides, sort, fill map. So we just ended up with a bunch of extra stuff in part 2, which was like parse input. All of these, you know, top right, bottom left. You know what? I feel okay about putting those together. Rotate and flip as well. I would put together just for readability's sake. Here we go. And you know what I'm going to do? I'm just going to copy that and I'm going to put it over here. I'm just being kind of like, I don't know, a little pedantic at this point. Not that this matters. Not that anyone's ever going to look at this code in the future. Maybe. Maybe they will. Maybe people will read it. But and I hope Literate CoffeeScript makes it slightly more readable. I think it does. But then again, I'm biased because I wrote it. Cool. So I'm going to, whoops. No, how do I do this? Like that. There we go. Get X. I'm going to commit day 20, and it's in the bag now. Day 20. And then I'm going to add to the README. I gotta find, what was the original day 20 link? It was the YouTube ID. There we go. Monster messages 20. YouTube. That was the original ID, and this is oh, you know what? These indexes are no longer correct. I don't think. I wonder if we even need these indexes. I don't think we do, honestly. I'm gonna find that out though. Here, I'm gonna put one in and just see what this does, because it should be the video. I mean, why would it need to know what the index is? Yeah, where are we? Yeah, it absolutely does not need to know what the index is. So I don't even know why we're bothering with these indexes. Okay, cool. And what was this called? This was called Jurassic Jigsaw. Jurassic Jigsaw. I think it's probably, no, it was the same size, a little bit. Okay, Jurassic Jigsaw, day 20, cool. And let's commit that. Yep. Day 22, README. Cool. And I will see you either
today or tomorrow for day 21, at least part 1, and then we'll play it by ear. But for anyone who's stuck around this long, thanks for sticking around, and feel free to chat. I appreciate the company, honestly, and I appreciate hints along the way. So if you got them, share them. Anyway, see you tomorrow or later today. I'm not sure.